Hello and welcome to the Superposition Guys podcast. My name is Yuval, and my guests today are co-founders of Planckian, Michele Dallari, CEO, and Marco Polini. Michele and Marco talk about their company's novel superconducting chip architecture, which uses global control and always-on ZZ interactions to drastically reduce wiring complexity and improve scalability. They discuss the advantages of controlling many qubits with just 2 or 3 classical lines, their early-stage experimental progress, and the software adaptations required to compile algorithms for their architecture. We also touch on Italy's growing quantum ecosystem, Planckian's collaborative approach to chip manufacturing, their excitement about recent advances in pulse engineering to compensate for fabrication imperfections, and much more. We hope you enjoy this episode. Hello, Michele. Hello, Marco. Thank you very much for joining me today.
Hi. Hello. Hi, glad to be here.
So, Michele, who are you and what do you do?
Yeah, so I'm Michele Dallari. I'm a co-founder and CEO at Planckian, helping Marco and Vittorio, two other co-founders, shaping business and helping the company grow in the quantum computing space.
What does the company do?
So as a company, we are a quantum computing company. We are developing a new quantum processor architecture, try to solve some of the most relevant scalability challenge that in superconducting computer, such as the wiring.
Is it focused on a particular modality, superconducting qubits, for instance?
Yeah, so thank you for asking. We have a clear mission as a Planckian. We want to build a core technology that enables quantum computers to scale to meaningful size by design. And we want to do that with a distinct approach. So rather than introducing new qubit modalities, we develop a quantum chip based on the most known superconducting chip design, which is the Trasmon. However, our architecture fundamentally redefines how quantum information is processed, enabling a significant reduction in control requirements by having multiple qubits controlled by shared control lines and allowing complex, not trivial multi-gated operation. So our vision is that by minimizing control complexity and maximizing also algorithmic efficiency, we can build a cornerstone for future large-scale quantum computing platforms.
Marco, I'm curious. Sounds like a great idea. Obviously, the number of wires in a superconducting architecture seems to be a limiting factor. Why is not everyone doing that?
Well, that's a tough question. Interestingly, in the history of quantum computing, that's the way things started. There was a very nice little paper on science that was published by Seth Lloyd in 1993, and it's precisely about, of course, a general idea, not yet really, practical and pragmatic, but it's a general idea of doing quantum computation by using global control. So Seth had this idea back in 1993. But then, how humankind proceeds, especially physicists, right? We don't understand complicated things. We want to start building by understanding very, very well building blocks. And that's where we started from. So, people began to work on a single quantum bit, a single qubit, fabricating that, and then, go using a bottom-up approach, adding a second qubit, then a third, then a fourth. And through this, bottom-up approach, you end up in a dead end, in our opinion, in the sense that you face this wiring and problem that really dramatically hampers scalability. So there are other people working on this. I think there are with other platforms, not the superconducting platform. But I think the idea is spreading, and it will spread. This global control that Michele was talking about, and will spread pretty quickly.
Could you explain, one of you, how global control works?
Right. So, okay. So I can give it a try. So essentially, the idea is the following. So imagine you have an ensemble of qubits, right? Technically, not a general number of qubits, and you can partition them into, let's say, 2 families. So the qubits are nominally identical, let's say, but I subdivide this family of qubits into two subgroups. And so all of the subgroup A, let's call it, is all the qubits are controlled by connected to a single external classical control line. And family B, which is the other half of the qubits which are left in the picture above, they are connected to another control line. Okay. Then there are special qubits in the entire group of qubits. There are special qubits where you can do single qubit, 2-qubit gates, and we have even invented architectures where you can do multi-qubit gates, for example, like single shot Toffoli gates. So essentially, via classical external pulses, you can move quantum information around in these architectures and then perform local unitaries, so single qubit gates, 2-qubit gates, or one-shot Toffoli gates, just by using classical control lines, like 2 classical control lines. So that's more or less, the gist of the idea.
The system, I would guess, still needs to be cooled to at least millikelvin temperatures, right, for the superconducting to work in the first place.
Right, absolutely, yes. But that's precisely the issue, right? Because as you know, right, you're bringing down many control lines. So in an ordinary locally controlled architecture, you have to bring down from room temperature down to, let's say, 10 or 15 millikelvin. You have to bring down 2/3 control lines per qubit, and that brings a lot of thermal load. So you have to spend a lot of energy trying to keep, temperature of the dilution fridge sufficiently low.
Yes, I know. I work for a neutral atom company, and when we explain the issues with controlling superconducting, I usually say, look, imagine if you had a 4K television and you open it up and saw that there are 2 or 3 wires going into every pixel. That would be one heck of a heavy and expensive and large television, right?
Right.
What is the status of the technology, right? Your technology right now?
Maybe
Yes.
Michele.
Yes, well, thank you. So we are in the stage where we are fundamentally experimentally testing the building block of our chip architecture. So as we come with a new chip architecture, basically that's a specific building block. I don't want to deep dive too much on that, but and disclose too much. We are fundamentally they are more or less related to how you couple the qubit together and how you can scale them in a full chip. And this is our near-term milestone, I would say. And our near-term goal is to prove that this principle can work in a basic chip design, and of course, in the long term, to scale it to more meaningful size. So we are basically, yes, in a very preliminary experimental point of view. We are very humble, very technical, experimental oriented. So we just don't think too much about the product as of today, more about the risk and the technology and the risk and the science behind that.
One of the questions that comes up in superconducting qubits is connectivity. How many qubits are connected to each individual qubits in your design?
Right. So, so the design requires qubits connect, so that each qubit is connected with, pairwise interactions to nearest neighbor qubits. Right. So it's it's 2 body interactions of a special type. That's a distinctive feature of our current architecture, in the sense that usually, like normal locally controlled quantum computers based on superconducting qubits, rely on swap type interactions. We require instead, we work in fact with longitudinal ZZ interactions, which is usually something you don't want in an ordinary architecture. It's something that people try to minimize, but so it's something bad there that we try to use to our benefit. And so we want to work in a regime in which this pairwise strong ZZ, this ZZ interaction is really strong.
Could I think of your design like a chessboard in which the black squares are, say, connected to one control line and the white squares are connected to another control line? And this way I could perhaps create with 2 control lines an interaction between any white square and an adjacent black square. Is that a correct way to think about it?
Partially, almost everything is correct. So let me put it this way. So you don't create, so the other good thing about our architecture, I think, is that we use always on interactions. So we don't use external classical controls to engineer and tune interactions between qubits. Those are to be native interactions that you produce a fabrication level. So we do designs which maximize the Z interaction. They are there, but the partitioning of black family and the white family of qubits, that's perfectly fine. And you use the controls to move quantum information around and carry out logical operations. But the interactions are always on. They are static interactions.
If you think about your initial chip, can you provide some numbers? How many qubits you expect to have there, and how many control lines in total will you need?
Okay, I can go. Yes. So we are currently, worked with the companies that fabricate chips for us. So we're currently at 5 qubits. But these, I'm referring to these stuff that Michele was talking about. These de-risking technology. So we are now working with 3/5 qubits in total. And we are in fact emulating a global control by a local control, but eventually we will grow up this. It's just to risk the building blocks. For example, check how strong is the nearest neighbor interaction that we were talking about earlier.
Once the de-risking is done, and let's assume you try to build a chip with, say, 100 qubits, how many control lines would you expect that to have? Only 2 control lines?
So that's a principle. I mean, this is so I'm sorry because I'm a theoretical physicist. But so let me discuss about principles, and then we can deep dive and see whether there are technology limitations. But in principle, the beauty about this is that if you scale from 5 qubits to 10 to 100 to 1,000,000, in principle, you need only 2 control lines, 2/3 maximum control lines in our design. So that's a beauty. So the number of lines does not scale thermodynamically with increasing the number of qubits, but it's always order 2, 3.
Every approach has disadvantages. What would you say, Michele, are the disadvantages of the approach that you are pursuing?
Yeah, first of all, as a first mover, I will say, of course, there are a disadvantage and challenging. There are some technological disadvantages, which are more related to the challenge that we already envision that we need to face. Is, of course, as Marco told, this is principle is an architecture that scales with a fixed number of control lines. From a technological development point of view, we might know this come with some challenge that we need to face. So probably we need a little bit more control line than expected in order to our architecture properly works. And of course, second one, and that we are already solving that, is how we can properly engineering the control of this architecture in order to reduce also to maximize the computational efficiency of the platform. Then, of course, there is a business side, and also we are a newcomer in the spaces. We are working very mature, let's say at least one of the most mature qubit platform with big play out there. And so it comes also to questioning about what kind of potential business model we want to focus on and how we can fit in the large, let's say, vision of how this industry is maturing. And this is very interesting for us because we are coming up from a nascent ecosystem, which is Italian one, where new stories are maturing and also new business model can be developed around this technology. So I think that one of our main feature, I will say, that is we don't work at the qubit design level, more a chip architecture level. So we can leverage some freedom here in the space also from which can be exploited also from this business perspective.
Do you expect gate fidelities, single qubit, two qubit gate fidelities to be on par with traditional superconducting designs?
These are our KPI. So one of their near term KPI is to understand how this architecture impacts in terms of gate fidelity for one qubit gate, 2 qubit gate, or rephrase it differently. We want to maximize our chip packet in order to be on par with the state of the art.
Does one need to design the software differently to take advantage of your algorithm? So if I have a Qiskit program, does it need to be compiled completely differently to run on your future computer?
Yeah, that's a very good question, Yuval. And as I mentioned, we are working at chip architecture. This is a very, let's say, nascent also technology. We recognize that this come with interdependency of play with different level of the stack. And specifically, the closest one is the middleware and the firmware. So yes, probably, and I'm sure about that because we are working already on that, that there needs to be some work that has to be done from a compiling point of view, how we can compile high-level algorithms in our chip architecture. We are working on that. That is come with the development of a quantum simulator based on our chip architecture. But the goal here is to close the gap and use as much as we can the software ecosystem that is already been developed, at least in the superconducting community.
Can you share some information about the company? When were you founded? How large are you? Where are you based? How is funding a
Sure.
for this company?
Yeah, sure. So we are a little less than 20 people as of today. We launched the company in 2023 with a pre-seed round from many Italian investors with some international investors. We grow pretty fast considering where we are based, from 3 to 20 people in less than a year, 80% which PhD, as I think is pretty common in this spaces, with 4 nationalities. And this is something I want to align because we are an Italian-based company. We are based in Pisa, which is a long-standing tradition of rich ecosystem in terms of research activity in space. We are the first joint spin-off for 2 leading institutions there, which are University of Pisa and Scuola Normale Superiore. So we are, as of today, based in Italy. We recruit and we bring some talent which were abroad back to Italy, and we've been able to recruit it from international pool of talent. So we are, pretty satisfied where we are when we're standing today.
The company name is Planckian. Any particular reason?
Well, H bar, right? Everything we do, everything we do has H bar. So I don't see any other good name for a quantum company. So this is the best. It's difficult, of course, but to pronounce maybe a little bit. Somebody forgets a K and so on, replaces the K with an H and so on. It's Max Planck. Come on, we have to honor tradition.
But Max Planck was German, I think.
Right. But fermions we have already used. We have Italians are associated with more fundamental stuff, and Olivetti had already been used for classical computers. Then so why not borrowing? We are in Europe at the end of the day, so that's what we I think that's new generations and our stuff. We have to think in terms of being united too. So nothing bad in borrowing German scientist names.
How is the Italian quantum ecosystem? Is it is it rich? Do you see many other quantum companies, or is it primarily focused on academia? What can you share on that respect?
Yeah, I would say that Italy has, let's say, historically benefited, as speaking from myself, then I will ask Marco to add something here, but Italy has historically benefited from a strong scientific ecosystem, but has often struggled to translate research into technology and successful ventures also. There are several factors that contributed to this. Some are cultural, some are related with chronic underinvestment in applied research, which is essential to the scientific advances and prepare for the commercialization. In the last couple of years, there have been some interesting ventures, especially in the quantum space, that have been emerged. Without naming ourselves, but there are other players that's coming out as very interesting activities, and we cheer from them as we hope they cheer from us because it means that the ecosystem is growing. Plus, there is Italy has worked intensively in the last couple of months to develop a national quantum strategy, which has been released in February, and there is an open consultation ongoing. We contributing to them, and we pleased that much of the suggestion that we, as an industry player, share with the government have been accepted. So I think that we are coming later to try to close the gap. So and this is, it's something that we really push for that, as we believe that it was critical for the quantum ecosystem to emerge, at least in Italy.
How soon can I use your chip?
The soonest, hopefully. The soonest.
Any expectation on when it will be ready for people to try out?
Let's say that as of today, we are focused on the risk in the building blocks, so and developing, which is a basic chip, but it's not something we want to put in the hand of the customer. Yes, in the next couple of years, this is our goal, is to develop something that we can have people use it and experiment on that, and from us also gathering data about how we can our kit to perform with the rest of the technology out there. So yeah, this is the basic timeline that we can share as of today.
You've been doing this, at least in the context of this company, for the last 2 years. What have you learned recently? What do you know today that you didn't know, say, 6 months ago about this technology, about the industry?
But I can answer technically. I mean, so one particular thing, so when you build a solid state architecture, there are lots of issues with fabrication, right? So because it's not like neutral atoms, or they are all identical by nature, right? So when you build qubits, so the level spacings are a little different. There's going to be inhomogeneities in this coupling, nearest neighbor coupling between the qubits. There's going to be lots of and so we were pretty worried about this, because we were, in our ideal calculations, as you said, 6 months ago, these features we were a little scared about this, but now, like, we have, a digital emulator, and we know how to solve these problems. So compensate, for example, with pulse engineering, these artifacts that are there in real life. And so, those are things that we were really worried about 6 months ago, but now we are very confident. And so you were asking Michele earlier about gate fidelity, for example. So the digital twin says that, these artifacts and inhomogeneities can be compensated with optimal control strategies. And we are very happy about that. So we didn't sleep now.
Anything to add to that, Michele, on things that you've learned?
Yeah, to me, I was really surprised, amazed how the quantum industry is open and collaborative compared to other industries. So I came from a different experience. So I work in energy sector before, then I work for the government. I work in another DTech sector, but I've been really surprised about how collaborative is this ecosystem. Also from different players that you can see from a side that look like competitors, but in reality they want to build this amazing technology because they are the first user. They want to be the first user of this technology. So this is something that I learn, and I'm constantly amazed by that. Actually.
Where would the chip be manufactured?
As a new newcomer industry, want to be, let's say, have also a different approach to the market. So we try to be as collaborative as possible with other players. So as of today, we have different partners that are manufacturing our building blocks, and also we design in-house. So we want to keep the core IP in-house. Then we have a selected partner that we are working with from the manufacturing point of view, and then we're gonna test either in-house, and we have different also partner in the testing. We want to accelerate these R&D phases, and this is what we have done today. Then in the future, there are different options we are assessing and considering. But of course, we want to keep as much as possible in-house in terms of core value, but at the same time, we want also to collaborate as much as possible with partners, because we think that is also an opportunity for us to have our technology tested and assessed by industry.
And last, I wanted to ask you a hypothetical. If you could have dinner with one of the quantum greats, dead or alive, who would that person be?
Oh, that's very super. Yeah, it's a good question. I think maybe you allow me to name someone who is not related to the quantum. But to me, Thomas Edison is the prototype of inventor, and I think that it's really someone who I constantly be inspired by.
How about you, Marco?
But definitely a scientist. I mean, how about Max Planck, right? So, given our name, no, it's a very good question. Many people, but probably people of the caliber of Peter Shor. It would be very nice to have to have a discussion. I would be very happy to do that.
Very good. Michele and Marco, thank you so much for joining me today.
Thank you, Yuval.
Thank you, Yuval.